talk will be on Laconic function evaluation and applications. It's a joint work between Willy Quash, Hotek Wee, and Daniel Wicks, and Willy will be giving the talk.
Thanks. Can you hear me if I speak? Okay, cool. Yeah, so I'll talk about Laconic function evaluation, which is a cryptographic primitive we introduced with Hotek Wee and Daniel Wicks. So let me dive straight in and tell you what it is. So for that, imagine the following situation where you have two parties, Alice and Bob. Alice has a function f, Bob has some input x, and Alice wants to compute f of x. So we are doing crypto, so the thing we're hoping for is that Alice doesn't learn anything other than the output of the computation. So in other words, we don't want Bob to directly send over x to Alice, and Alice to compute everything on her own. So to do so, Alice will process her function in a certain way and publish some information that depends on the function in the sky. And using this information, Bob will be able to encrypt his input x under this digest and send it over to Alice, and hopefully Alice will be able to use this ciphertext to retrieve the output of the computation. So what do we want? If we want security with respect to Bob, Alice's digest should depend on f. Otherwise, from Bob's point of view, everything Alice could have acted using a completely different function. On the other hand, the encryption should hide x. That's pretty much what we want. But still, from what I said, nothing prevents the digest to be the function and for Bob to compute directly the function. So to make the primitive interesting, we add another requirement where you can imagine the function that Alice has to be huge. And for Bob, and we pretty much regard that Bob doesn't do the work of computing f. So you can imagine, for instance, that Alice is Google, and is the only person who is able to run f, and that Bob is playing on a quite outdated phone and is not able to run the function. So if you consider the function as being a huge circuit, just Bob is not even able to read the function. So Alice should do some work in order to compress down a huge function into a small digest that Bob should be able to read in order to encrypt. And even given that, Bob's work should be small, and ideally only depending on his input length. So that's pretty much what our primitive is designed for. So Laconic function evaluation, or LFE, is defined by several algorithms. The first algorithm is a compression function, which will take as input a function f and will output a compressed version. Notice here that I require the compression function to be deterministic. This will be useful later. I'll get back to it. So if Alice publishes, say, in the sky this digest, you can pretty much think about this digest as a function public key that any Bob can use to encrypt his input using some encryption algorithm. So this will give a ciphertext that Alice will be able to decrypt using her knowledge of f. So notice here that Alice, to compress her function, doesn't use any randomness, and therefore she doesn't have any secret state that is tied to the primitive. So here, actually, the decryption is public as long as the party knows the function f that x has been encrypted with respect to the same function. So this is strange, but this will be useful later. So we require several properties from our new primitive. First, that is correct, in the sense that Alice should retrieve the output of the computation. It should be efficient. Again, in the world where the function is huge, Bob should still be able to participate in this kind of protocol. So we require both that the digest should be small if the function is huge, and that Bob's work should be small. So in particular, the encryption time is small, and the ciphertext that Bob sends should be also be small. Notice here that this is at the price of having both the compression function and the decryption function to pretty much require to compute f. Okay. And for security, again, we require that pretty much everything that Alice does by seeing the ciphertext should be the output of the computation. So another property, so before that, notice that if the compression function is compressing, and so there exist collisions, and if Alice finds collisions, so that the digest are equal again, she can use the decryption function over there on both functions f1 and f2, and actually retrieve both outputs of the computation, so this is bad. So in other words, the compression function has to be a collision-resistant hash function, and therefore you need a CRS over there. So that's just syntax, and I'll omit the CRS as an input through the algorithm, but implicitly it's there. And the last property we might want is that for now, we only require security with respect to Bob. What if we require also security with respect to Alice? We might want that the digest actually hides F. So for now, this is definitely not the case because the compression function is deterministic. So we consider a variant of Laconic function evaluation where Alice's will use some randomness to randomly compress the function into a digest. But then if you want the digest to hide F, Bob shouldn't be able to use the decryption algorithm. So in some sense, Alice has to keep this secret state in order to decrypt now. So decryption is now secret. Okay, so let me tell a bit about why we need such a primitive. We have already so many cryptography primitives around. So a natural thing that looks extremely similar to Laconic function evaluation is succinct functional encryption. So first, let me tell you what it is. In a succinct functional encryption scheme, the same way you have Alice with some function f and Bob with some function f, some input x, sorry. And you have some trust party, say Carol, that were able to issue Alice with function secret keys. At the same time, she will be able to produce some public key and give that to Bob. And notice that the public key doesn't depend on the function f. So here, Bob, using the public key and some input x, will be able to produce a ciphertext that Alice is able to decrypt using her function key. So the primitive is extremely similar to Laconic function evaluation in the fact that Bob's work is small. That's pretty much what the succinct here means, in the sense that everything that Bob does is efficient. Everything he touches is small, and everything he computes is efficient. So the main difference here is really that in order to do such a thing with succinct FE, you really need a trusted third party. Why do you need that? Because pretty much the trusted third party here has some trapdoor that actually allows her to break the security of any ciphertext produced under this public key. So on a higher level, we can think of functional encryption as dealing with function secret keys, and the ciphertext is not tied to any function. So in particular, if you are given the appropriate function secret key, you can compute any function on the input encrypted in the ciphertext. And by comparison, for LFE, we don't require such a trusted party because Alice can do all the job. And we deal pretty much with function public keys. So we give Bob a function public key that is short, and this will tie the ciphertext to the input he's encrypting. So no one should be able to retrieve anything else than the function, that the output of the computation. It turns out, interestingly, that actually LFE implies single key succinct functional encryption in a generic way. So the main results that we prove in this paper, apart from the, defining this new notion of Laconic function evaluation, is to actually build it. So we build it under the learning with errors assumption. And to be a little bit more precise, we'll build a scheme that satisfies some kind of selective security, assuming some exponential ratio from modulus to noise in the LWE problem. And if you like parameters, those are the parameters if you want to read. But pretty much what's important here is that the only blow-up in the encryption and the ciphertext size only depend polynomially on the depth of the circuit. So if the circuit that Alice wants to compute has some depth d, everything only depends polynomially on the depth and not on the size. So if the circuit is really wide, we can gain a lot. Also, we prove a stronger adaptive security notion from an assumption that I will not describe here, but we think is pretty natural, that we call adaptive LWE. As a second contribution, we show actually that the standard notion of Laconic function evaluation that I talked about with deterministic compression actually generically implies statically function hiding, where the digest actually hides the function statistically. And last, we give some application to motivate the introduction of such a primitive. So in this talk, in the rest of the talk, instead of talking about the construction, I will try to convince you that this primitive is actually useful, and I will talk about some applications. So as you might have noticed, this cryptographic primitive is pretty tied to MPC and multi-party computation and two-party computation. So let me start with giving a direct application involving two-party computation. So the setting is extremely close to the one before. Alice and Bob now have some respective input xA and xB, and they want to compute some function that they both know on their joint input. It turns out that if you want to do that generically in a secure way, you need two messages. So without loss of generality, Alice will send the first message, Bob will answer, and Alice will recover the output. So security here should mean that both of the parties shouldn't learn anything more than their outputs. So in other words, Alice shouldn't learn anything about Bob's message other than the output of the computation, and Bob shouldn't learn anything about xA. Again, so this is possible, this has been shown to be possible more than 30 years ago. What we're interested in here is to have some setting where the function is actually hard to compute. So we would like the protocol to be short. So we would like, ideally, the communication of the protocol to be, say, much shorter than the size of the function. And we would like also the party to not work a lot. But of course, someone has to do the work if we want to compute the function in the end. So we would require at least one of the party to not do any work at all, pretty much. So that's what we are hoping for. And it turns out that, so as a warm-up, we can consider some what we call Alice-optimized protocols, where pretty much Alice is inefficient, she runs on a phone, Bob is Google, he has a lot of power, and Alice wants to learn f of x is b. So a very simple protocol, if we didn't care about security, would be simply for, this is what we want, would be to have Alice send her input, Bob compute on this input and send it back. And it turns out that we have the secure analog of that. And this is by fully homomorphic encryption. So if you know about fully homomorphic encryption, you pretty much can run this protocol homomorphically, and it will give you what you want. So what about the other case? Just before that, in the fully homomorphic case, Bob does all the work. It actually doesn't matter whether Bob input is large or not. It doesn't change anything about the protocol. So what about the Bob optimized protocol? It turns out that we didn't really know how to do that in a secure way. So again, with a loss of generality, Alice is sending the first message, Bob is answering, and Alice gets the output. And we want pretty much that Alice does all the work about f, and Bob does nothing. So again, we would want that the length of all the messages that are communicated should be small, and Bob's work should be small as well. And a simple protocol, if we didn't care about security, would be simply to have Bob send his input to Alice, and Alice compute everything. But it turns out that we really didn't have any secure version of that. Well, it turns out that with function hiding LFE, we have a direct solution to that, where Alice will start by compressing the function that expects Bob's input and spits out a digest that she will send to Bob. Bob will encrypt with respect to the digest his message, and Alice will be able to compute the output. So what happens here, again, by definition of our primitive, if the function is large, even if the function is large, Bob's work is small. So we have all the efficiency we want. The digest, both the digest and the ciphertext are small. So the protocol, the communication in the protocol is small, and the ciphertext is efficiently computable. Here, again, symmetrically to the fully homomorphic case, we don't care about Alice input length. So if it's large, the protocol is the same. So why is such a protocol secure? Again, by definition of security, from Alice's point of view, the ciphertext can only reveal the output of the computation. From Alice's side, again, if we use a function hiding version, well, by definition, the digest will hide the function fa, which has Alice's input hard-coded, and therefore will be secure from Alice's perspective against malicious bubs. Okay, so as a second application, let me switch gears and talk about general multi-party computation, where you have arbitrarily many parties, x1 up to xn, with inputs x1 up to xn, and they want to interact and in the end compute some joint function f that they all know about x1 up to xn. So the setting is we're interested in, again, is where the function is huge, the input is short, and we would like the protocol to be efficient with respect to the large function. So what can we hope for? We can definitely hope for low communication. Actually, some kind of those results already existed before. But what we're interested in is, again, to have parties perform a low amount of computation during the protocol. And of course, they do have to perform some computation because they have to compute this huge function in the end. But we can hope for having a protocol with low online computation, where the computation performed during the protocol is actually small. So this seems a bit contradictory, but actually Laconic function evaluation directly does that. So here we use the standard notion of Laconic function evaluation with deterministic compress, where we ask, say, all the parties to compute such a digest deterministically. But notice that all the parties know the function, so this can be done in an offline phase. This is expensive, but we don't mind. And then they pretty much want to compute an encryption of their journal input with respect to these digests. So Laconic function evaluation does not allow to do that. But now we can run a standard MPC that is not necessarily efficient to compute this quantity because encrypting is efficient. So this is an online phase. But again, even using a standard MPC that is not necessarily efficient, this will be efficient by construction. And now everybody can decrypt. And here I use crucially the fact that the compression function is deterministic so that the parties don't need any secret state in order to recover the output of the function. So again, what do we get? We have some extremely costly offline phases, which correspond to a preprocessing phase and some post-processing phase, which actually depend on the complexity of the function. But the online phase is extremely efficient, even if the function is huge. Okay, so to conclude, what we do in this paper is to define what we believe is an extremely natural cryptographic primitive that has not been defined before, that we call Laconic function evaluation. We give a construction from the learning wizard's assumption. We show some relation between different variants, where we show that a deterministic version generically implies the statistical function hiding one. And we give some extremely simple applications that solve problems that were natural and open since then. Thank you very much for your attention.
Questions?
Yeah.
in a semi-honest model, probably, right?
Yeah, so pretty much in everything, of course, Alice can lie and send like not send the correct address, but that's not something we can like really handle. That's like pretty much inherent, because if you want to verify what Alice does, you need to pretty much just do the work of Alice. So you pretty much assume that all the parties run honestly.
Yeah, so presumably the secure computation results are secure not in a malicious adversarial model, but in this like semi-honest model.
And yeah, if she sends the data with respect to the identity function, Bob security doesn't hold anymore. Also, so. But yeah, she can learn like pretty much anything she wants.
Actually, I have a question. Can you actually say something in the opposite direction? Is there a connection, for example, that this like a succinct two-party Bob optimal secure computation implies something like your function hiding LFE?
So I'm not sure, in the sense that in our case, so I won't commit that much, but I think that in our case, the first message is reusable and everything, which is not necessarily true in general. I'm not sure. I won't commit.
So yeah, we can ask afterward. Any further questions? All right, let's thank Willie again.